Hi friends, today I'll be explaining Physics May June 2016 paper 61. Question 1 states a student is determining the weight of a meter roll using a balancing method. The apparatus is shown in figure 1.1. A. The student places the load P on the meter roll at the 5 centimeter mark. She places the meter roll on the pavement at 45 centimeter mark. She places load Q on the roll and adjust the position so that the meter roll is as near as possible to being balanced. She measures the distance x between the center of the load P and the pivot and the distance y from the center of the load Q to the pivot. She repeats the procedure placing the load P at the 10 centimeter mark, at the 15 centimeter mark, and at 20 centimeter mark, and at the 25 centimeter mark. The readings are shown in table 1.1. So we have these readings over here. Then over here we have all these readings. Then part 1 states for each value of x calculate A is equal to px, where p is newtons, 1 newton. Record the values in the table. P is the weight of the load. So we have to calculate the value of A. So where A is equal to px. So A is equal to px. So the value of P is 2 newtons, which is 1 newton, and multiply by x, which is centimeter. So this will be newtons per centimeter. Then over here we will multiply P, which is 1, multiply by x, 40, which will be 40. Then 1 multiplied by 35, which will be 35. 1 multiplied by 30, which will be 30. 1 multiplied by 25, which will be 25, and 120 multiplied by 20 will be 20 centimeter. And over here we will write A. The value of A is, units of A is newtons per centimeter. Then for B, for each value of y, calculate P is equal to Qy, where Q is equal to 0.8 newtons. Record the values in the table Q. Q is the weight of the load Q. So we will multiply Q by y. So the value of Q is 0.8. So 0.8 multiplied by 42.5, which will be 34 newtons per centimeter. We will write newton per centimeter over here also. Then in the second one, 36 multiplied by 0.8, which will be 28.8. Then 0.8 multiplied by 30, which will be 24. Then 0.8 multiplied by 24, which will be 19.2. And then 17.5 multiplied by 0.8, which will be 14. So these are the values: 34, 28, 20, 28.8, 24, 19.2, and 14 for B. And for A it will be 40, 35, 30, 25, and 20. I set these values in opposite direction. Part 2 states complete the column headings in the table. So for x it will be centimeter, and then for y it will be centimeter. Then for A it will be newtons per centimeter, and for B it will be newtons per centimeter. Question 1 part B states plot a graph of A per, which is newton per centimeter, y-axis against B newton per centimeter at x-axis. Start both axes from the origin 0, 0. So as we have calculated the values of A and the values of B, so first we will plot the point of 40 of A and 34 of B over here, which will be over here. Then in next distance, which is 35 centimeter and 36 centimeter, we have 35A and 28.8B. Then over here it will be at this point. Then for the third measurement, third mark, it will be 30A, 30 centimeter newtons per centimeter A, and 24 for B. So it will be over here. Then for fourth mark it will be 25A and 19.2B, which will be over here. And then for the fifth and last mark, which is 20A and 14B. So this will be over here. Then you will use a ruler and draw a straight line joining these 5 points and make it to the origin, where it will be 5 or 6 on A of A and 0 of B. Question 1 part C states, using the graph determining the vertical intercept y, show clearly on the graph how you obtain this value. So we connected these all 5 points and it is between 5 and 6. So this will be 5.5 on y axis, which is A. So we will write the value which is obtained, which is vertical intercept of y, which is 5.5. So we write 5.5 as the final answer. Then in part D, it states, calculate the weight W of the meter rule using the equation W is equal to y divided by z, where z is 5 centimeter. Then we have already calculated the value of y, which is 5.5 centimeter, 5.5, and the value of z is 5. So we will write 5.5 divided by 5, which will be 1.1. So the value of the weight of the meter rule is 1.1. And then in part E states, suggest one practical reason why it is difficult to obtain exact results with this experiment. So the answer will be, it is difficult to keep the meter rule balanced, as the question is of 1 mark. So we have to write one statement, which is, it is difficult to keep the meter rule balanced. Question S states, the student uses an accurate electronic balance to obtain a second value of the weight of the meter rule. The weight obtained on the balance is equal to 1.24 newtons. State and explain whether the two values of the weight agree within the limit of experimental accuracy. Statement: agree, they do. Justification: the first value is 1.2 newtons and the value is to 1.24, so both are close enough within the limit of experimental accuracy. So yes, the statement is agreed and they do, and so the justification will be, the first value is 1.2 newtons and the value is 1.24 newtons. Both are close enough within the limit of experimental accuracy. Question 2 states, a student is heating water in a beaker using the electric heater. He measures the potential difference V across the heater and the current I in the heater. Then question states, write down the readings shown on the meters in figure 2.1. So the value of V over here is more than 8 and less than 9. So there are 4 points, 1, 2, 3, 4. So it's on the first point, so it will be 8.2. So you write 8.2 volts, and then in ammeter it is more than 0.4 and less than 0.5. So it is between 0.4 and 0.5. So it will be 0.45, which will be 0.45 amps. So 8.2 volts will be for V and 0.45 amps will be for I. Question B states, he measures the temperature of the water before heating. Write down the temperature reading delta shown in the figure 2.2. So the mercury is below 20 degrees, but it is only 1 degree less than 20. So this will be 19 degrees, and we'll write 19 degrees Celsius. It is important to write the unit. So if you don't write this unit, you will half mark will be deducted. Question C states, on figure 2.3, draw a line and an eye to show clearly the line of straight side required to read the volume of the water in the measuring cylinder. So you have to draw a perpendicular line on the measuring cylinder over here and put 90-degree mark, and make an I over here and write a statement which is I must be perpendicular to the scale and read bottom of the meniscus because there's always an upward curve of on the water edge, so it is better to read from the lower meniscus, bottom of the meniscus instead of top of the meniscus because this will add 1 centimeter cube to the reading of the water. Question 3 states a student is investigating the resistance of a lamp filament. The circuit is shown in figure 3.1. This is the circuit of lamp filament. Then in part A, the student places a sliding contact C on the resistance wire at a distance D which is 0.2 meters from point A. He measures the current I in the current I in the circuit and the PdV across the lamp L. He repeats the procedure using values for D of 0.4 meters, 0.6 meters and 0.8 meters. The readings are shown in table 3.1. Part 1 states calculate the resistance R of the lamp filament for each set of readings using the equation R is equal to V divided by I. Complete the column headings in the table. So we have to calculate the resistance for each distance. At distance 0.2 meters we have voltage of 1.6 divided by the I which is 1 using the formula over here which will be 1.6. Then at 0.4 distance we have 1.3 of volts V and then 0.86 of current. 1.3 divided by 0.86 will be 1.51 resistance. Then at 0.6 we have 1.0 divided by 0.74 which is 1.35 and then 0.8 of D which is at which it is 0.8 V divided by 0.66 which will be 1.21 resistance. Then in part 2 it states complete the column headings in the table. So the D which is distance is always measured in meters, so we will write amp, and then the voltage is always measured in volts, so we'll write V, and current is always measured in amps, so we'll write A, and for resistance we will write ohms. And so these will be the final values for part 1 and part 2. Question B states the student notices that the lamp does not glow when he takes the final set of readings. He thinks that the filament has broken. State whether the student is correct and give a reason for your answer. So over here in the table, as he increased the distance of the resistance wire from point A, the value of volts and current kept decreasing, and so the appearance of the lamp filament decreases, and from being very bright at 0.2 meters to dim at 0.6 meter, and at the last it does not glow at 0.8 meters. So whether the student's question states whether the student is correct or give a reason for the answer if the filament in the light has broken or not. The statement is no because there is a low current reading which is not enough for the lamp. Filament never gets broken at lower current, and hence it will break down if we give a high amount of energy to the filament. So the filament never gets broken at low current, and we will write the statement as no, and the final reason will be there is a low current reading which is not enough for the lamp. Filament never gets broken at low current. Question C states a student suggests that the resistance R of the lamp filament should be constant. Suggest referring to the observation a reason why the resistance R may not be constant in this experiment. So the filament changes brightness, and the increase or decrease or change in temperature of the filament will make the resistance not constant in this experiment. So these are the two statements that we have to write in question C. Question D, part 1 states name an electrical component that could be used instead of a resistance Y AB and sliding contact to vary the current. A variable resistor can be used. So for D part 1, the final answer will be a variable resistor. Then part 2 states draw the diagram of the current including the component instead of the resistance Y of this component instead of the resistance wire at the starting contact. So first we will put a power supply and then a switch, and then over here we will put an ammeter, and over here we will put a variable resistor, and then over here we will put a lamp, and below it we will put a voltmeter. So this will be the layout of the circuit, the diagram of the circuit, when we put a variable resistor into it instead of a sliding contact and a resistance wire. Question 4 states a student is investigating the effect of insulation on the rate of cooling of hot water in a 250 centimeter cube container. So student can choose from the following apparatus: a thermometer, a 250 centimeter cube glass beaker, a 250 centimeter cube plastic beaker, a 250 centimeter cube copper can, and 250 centimeter cube of measuring cylinder. Three different insulating materials, a clamp, pause and stand, and a stopwatch. Plan an experiment to investigate the effectiveness of the three insulating material. You should explain briefly how you could carry out the investigation. State the key variables that you would control. Draw a table or tables with column headings to show how you would display your readings. You are not required to enter any readings in the table. Explain how you would use your readings to reach a conclusion. So a diagram is not required, but you may draw a diagram if it helps your explanation. So in the diagram, first I will use a glass beaker with material 1, which is in material 1 we will use a glass beaker and three different insulating materials. In first we have material 1, then in second we have a plastic beaker with a material 2 insulator, which is our different. We can over here I have drawn in straight line. Over here I have drawn with a little zigzag, and then in third I have drawn the material 3 with a more amount of zigzag, so that there can be a difference between three different materials. And in third beaker we have copper can or beaker C. So I will explain how I carried out the investigation. So for investigation, first use same amount of water throughout the experiment. So this means that you have to start recording the value of temperatures of each beaker of all three beakers at the same time, so that the results or the experiment can be accurate. So this is for part statement 1. Then in statement 2, put hot water in each container and record the temperature fall at equal intervals. Then the key variable is same starting temperature, same thickness of each insulating material, constant room temperature, same volume of hot water in each container. So we have three types of key variable, which is same starting temperature, then same thickness of each insulating material, and constant room temperature, and same volume of hot water in each container. I know if you don't understand this writing, so you can tell me, and then I will put a subtitle on this. Then over here we will draw a table with columns and headings. So at each time interval, we will calculate a time interval in seconds. So 20 seconds, 40, 60, 80, and 100 seconds. Then the temperature of beaker A, then a temperature of beaker B in degrees Celsius and temperature of beaker C in degrees Celsius. And then I will draw a table over here. Then the conclusion of this is there is the smallest drop in temperature in beaker A, so it is the best insulator. Temperature drop in beaker C is largest due to, so it is not a good insulator as of beaker A. So we have to draw diagrams to show the temperature fall at each interval. So for beaker A it is constant, and then for beaker B it is dropping way higher as compared to A. Then beaker C temperature is falling at the highest rate as compared to B and A. So this will be the final diagram for the conclusion. Question 5 states a student determines the focal length of a lens. The apparatus is shown in figure 5.1. Here we have the apparatus that is shown, and then part A states a student places the lens at a distance u from the illuminated object. Then he moves the screen until a sharply focused image of the object is seen on the screen. Measure the distance u from the illuminated object to the center of the lens. So we had to calculate the distance of u. So you will use a ruler and measure the distance from here up till here, and then the distance between the illuminated object and the lens is 48 millimeters or 50 millimeters, as it's because of 0.2 is of difference between accuracy. Then in second question, measure the distance v from the screen to the center of the lens. So we will measure the distance from here up till the screen, which is 20 millimeter, and over here I calculated 21 millimeters. So 1 millimeter can be a difference due to experimental accuracy. Then part B states figure 5.1 is drawn 1/10 actual size. Calculate the actual distance u from the illuminated object to the center of the lens. So if the distance over here is 1/10, so we will multiply 48 by 10, which will be 480 millimeters. So the original actual distance of u is 480 millimeter. Then calculate the actual distance v from the screen to the center of the lens. So if in the diagram it is 20 millimeter, then you multiply 20 by 10, which will be 200 millimeter. So the actual distance v from the screen is 200 millimeter. Then question B part 2 states calculate the value f1 for the focal length using the equation f1 is equal to uv divided by u plus v. So u is 480 multiplied by v, which is 200, divided by u plus v, which is 480 plus 200 over here, which will be 141.2. So the focal length is 141.2 millimeter. Question C states a second student repeats the experiment 3 times using different lenses. His values for the focal length of his lens are shown in table 5.1. In table 5.1 we have, in first experiment he has 132 millimeter, in second he has 141, and in third he has 135. Calculate the average value of f2 for the focal length of this student's lens. So he will take the average of these three by adding 132 plus 141 plus 135 divided by 3, which will be 136 millimeters. So the average value of focal length will be 136 millimeter. Question D states a third student using the same method finds that the focal length of her lens is 200 millimeter. She reads in a book that when u is equal to 2f, the distance u and v are shown in figure 5.1 are equal. Calculate 2f of the student's lens. So 2f is the 2 multiplied with the focal length, which is 200, so which will be 400 millimeter. So the 2f for this student lens is 400 millimeter. Then then the student sets up the apparatus as shown in figure 5.2. She adjusts both x and y to the 400 millimeter. So she observes that the image is blurred. The student slowly increases the distance of y and obtains a sharply focused image when y is equal to 406 millimeter. Discuss whether the student results confirm that the statement in the book. Yes, 6 millimeter difference is very small. It is within the limits of the experimental error because in 6 millimeters there is a very small change. So this will not affect the student's results on the statement in the book. Question E states, suggest two precautions that you would take in this investigation in order to obtain reliable results. So I have written four precautions from which you can choose either two of them. So in first statement, it is use of darkened room. So this will obtain a reliable results. Then precaution 2 is mark position of the lens on the holder. This is a second precaution. Then third precaution is ensure object and lens are same height from the bench. And the fourth precaution is move screen back and forth to obtain the best image. So these are the four precautions that you would take in this investigation in order to obtain a reliable results. So you have to at least write, it is must that you have to write two precautions. So you can write any of these